Is this sorry. So recording. My name is Joshua Wang. I'm a researcher with PAST University. Today, we are very happy and honored to have Professor Wang as our seminar speaker today. Professor Wang is the chair professor of computational intelligence at the Department of Computer Science and Data Science at City University of Hong Kong. Before this position, he held various academic positions at Dalian University of Technology, Case Western Reserve University, University of North Dakota, and the Chinese University of Hong Kong. He also held various short-term visiting positions at multiple academic institutions. He is the editor-in-chief of the IEEE Transaction on Artificial Intelligence and the PAST, editor-in-chief of the IEEE Transaction on Cybernetics. He is an IEEE Life Fellow, IAPR Fellow, multiple fellows. He is a recipient of the APNNA Outstanding Achievement Award, IEEE CRS Neutral Network Pioneer Award, and a number of other awards. So today, let's welcome Professor Wang.
Thank you. Thank you for the introduction and invitation. It's my great pleasure to be here today in UC Berkeley to give a talk. In Chinese, we have something like a school brief to get a J, meaning I have something small, but you probably give some big word. I mean, last word. Anyway, I don't know if it makes sense or not. So my topic is general, but I try to narrow down a little bit application related to transportation or vehicle technology. I hope fit the program a little bit. We start with optimization. Optimization is an area, and we use optimization for problem solving, machine learning, data processing, transportation, and many things. Control robotics also, and we use optimization everywhere. Okay. So basically, we have a different paradigm for machine optimization. Machine optimization traditionally from OR or MS or mathematical programming, but it's progress slowly after 60 or 70. But we have a new paradigm, basically using an IR base. AI, our brain is a source of intelligence. Okay, so we do decision making every day, every moment, for perception or cognition and other big decisions. So basically, we want to map this dynamic process into a mathematical or physics model eventually to learn this to mimic the decision making process, so-called in quick way or more smart way. So we will design a model mathematically or physically eventually to optimize some given parameter, find an optimal solution or optimal solution change will follow. So this actually is called neurodynamic optimization. Okay, so starting with John Hopfield since 1986. Last year I went to US. I came to US for my PhD study 40 years ago. So basically in 1980, so we published a number of papers. Some of them still can be used, but nowadays under the new framework. So of course, this last year, both John and Jeffrey received Nobel Prize in physics. Actually, mentioning their work in the 80s, or maybe even later. Yeah, mostly 80s, their work on optimization, actually, physics in form, something like that. So optimization is generally can have a object function of either scalar or multi-vector value or with subject constraint. So many problems have been tackled over the last 40 years. Some of the problems have been solved, with many models, finding exact solution. For example, Hopfield already started in 1980, but sometimes his model is not perfect. So after 40 years, there are many models have been developed for linear programming, for example. Transportation problem, Chinese, Chinese postman, or maybe, yeah, shortest path is actually a linear programming problem, right? Anyway, it's a trivial, it's simple. Anyway, there are many other problems more less trivial, like non-smooth optimization, generalized non-convex, like pseudo-convex. I mean, many optimization problems are more difficult to solve, especially non-convex with non-convex object function or constraint. We have a global optimization problem there. Okay, so also with multi-objective is non-convex by nature, lastly, mixed integer combinatorial optimization with both continuous variable and the discrete variable. So those problems have been tackled last 40 years. Of course, been very successful. So for some of them, first few, the single neural network can find exact solution, optimal, no problem. But some problem like the distributed optimization or non-convex, mixed integer, we need a multiple model to work on because single model will start in local minimum or local solution. So there are many design principles used for design a neural network for solving optimization problem. The simple way that doing so is by using penalty function method, which is straightforward. How few and even Liang tried, UC Berkeley penalty in 1980. They also developed model for solving optimization problem, not in programming, for using penalty function method. Okay, they don't call smooth, but smooth is added by me. Also, some other methods in optimization theory, or fixed theory has been used for optimization, design neural network for optimization, like Lagrange method, duality method, predictive method, and also non-smooth penalty function method. So this is a small difference from there, only one small difference, but this big jump, because with non-smooth penalty function method, we can have a finite time convergence, or a fixed time convergence on that. So otherwise, we have a very long conversion time. And also we use some other principle like, principle, minorization, minimization, or minorization or maximization principle, so MX principle to design neural network for each cycle. And also lastly, but we also use multi-agent system theory and human intelligence method to design neural networks. Basically, we can expand the neural network from a group, more than one, a two is the minimum. So there we have a collaboration among neural networks. Okay, but first of all, we will find the individual neural network, but convert to all those local optimal solution. If in present non-convexity, okay, not every neural network will convert. Sometimes they will convert upside down stability to the density condition, of course, but not necessarily. So for non-convexity, many optimization model before, but that's assume the whole solution is the landscape is convex, but that is not always true. So we have to design neural networks to be sure stability of the neural networks because dynamic evolving. Okay, so this model we actually is 20 years ago with my students also. It's based on differential inclusion. Okay, so you can see of course assume the object function is not smooth. So if smooth it will be different equation. Okay, so this is the not smooth part. Okay, this is gradient. It's still gradient based. Okay, this is the steroid gradient. And also we have basically based on some other method, we have this different model for solving this. This is another one in 5 years ago. So based on augmented Lagrange. Okay, so basically we added two terms in Lagrange function to convexify, not more like convexify the function to make sure this convergence. Okay, of course, the alpha beta has to be larger than the lower bound. And also another one, this is the condition, because this sufficient condition satisfied. This is the minimum eigenvalue with the Lagrange function. Supposed to be a non-convex, this will be negative, so double negative, some positive. So anyway, this is sufficient condition for a local convergence. And also other model we developed without the using of Lagrange augmented Lagrange function. So without a Bayesian term. So, but using different time constant, sorry. Different time constant. So here you can see the epsilon one, epsilon two are different. So they have to move one slower, another faster. So this is of course with subject to some condition. So some condition is pretty simple. We derive sufficient condition. For the time constant, you can see if they are same, this is never true because this one is negative, right? Because this is the annual value of the singular value of the Lagrange. Anyway, so if this is different, then we make sure this is greater than zero. So we have another model. This is another one. I think, yeah, we also based on two-type skew and also visualization minimization principle. Slightly different, but they also have some other severe condition. But we show the time constant has to be larger than the lower bound. So this is some new work for the local convergence of the neural network for foundation. Anyway, but local convergence is not enough. We need a global optimal solution. So that is hard. So that is challenge. We don't have method to find a global solution for everybody, for every problem, right? But anyway, we have some of this framework using multiple neural networks, and these two, of course, larger, better as a super intelligent method. So yeah, more than one are needed. Okay, so we have different like partners collaborators work on a different area, different issue point, and also different model, different time constant. We can find different local minima. Diversity is the key in the global foundation, right? Single one will start in local minima. So here I call collaboration, could be information chain, or or simple we call and for example, we can use the particle swapping tangent method or some other method, heuristic method, to share information among the local convergence. This local convergence like some convert sample, then the second one expand the search process spatially with multiple model and also temporally with another iteration. After local convergence, we treat a sample and then for many model we share information, then find the issue, then we find a new meeting point, jump up to local minimum, find the more promising meeting point, then search again. So because better heuristic can help because they cannot guarantee stability or global convergence, but they can help us find a better initial point, right? So that's the key. So of course, this borrow the idea from evolutionary computation there. They use their single seed or the particles, our ends, but there are no much local mobility there. So here we have a neural network, they can satisfy constraint and also guarantee find the local solution. Actually, satisfy liquidity condition. So in root competition, they have a good idea, but not necessarily solution consistency problem or repeatedly problem. Sometimes good, sometimes not good, because they don't have a guarantee. Here we have some bottom line, guaranteed constraint satisfaction and also local automaticity. Then we have a different better initial points, then we can find a solution gradually. So basically we have this two layer architecture. For the lower layer, we have more than one neural network to search for optimal solution. Satisfy constraint. Hopefully, but definitely a local optimal. Then upper level we have a local convergence as a sample. Then we have a diagram again. Extend the searching process in a different loop, outer loop we call. In local loop is the neural network convergence. Outer loop is the iteration. Yeah, so multiple neural network we use for scatter search. Of course, start from different point with find the goal, and also measure heuristic or some other mechanisms can be used for reposition the search. Unless we have a local conversion, then this is a repeating process. It's like collaboration do this again, expanding the space spatially and also temporally. We can almost sure find an optimal solution. Okay, so this is the architecture. So usually, of course, we don't have prior information. We can start randomly. Then one next round we'll start with with sample local solution. We can do just another one. So in theory, you can prove this under some minor assumption, we can almost sure converge all those features. So this was actually proved in the paper 5 years ago. Anyway, so sometimes we also treat the spectral non-convexity. Non-convexity is a big class, right? That of course excluding the pseudo-convex, which is the generalized one, that is the easiest to deal with. But the still non-convex is a big class, many problems. For example, some class we call biconvex. We have two vectors for the x and y. If fixed x is convex. Okay, fixed y is convex, but the x and y together is non-convex. So that problem is biconvex problem. So in that case, we can minimize the spatial complexity, design a system called 2 plus with the 2 neural networks. Because this is y is definitely starting local minimum. We need a pattern, just like police control. We need a pattern, right? So they have coverage, they have so information. So this starting local when you can cover. Okay, so this will have to work in different time scale. Otherwise, it probably is starting in the same local minimum. Also, it's starting with different input points. Okay, this is the minimum we can use. Have to double the spatial complexity at least in order to proceed. But meanwhile, we have to purposely choose the time constant input point to avoid the prematurity. Okay, anyway, so this scheme can.
Sorry, before you move on, just curious on the biconvex problems here.
Yeah.
Are you able to prove convergence to a global minimum?
Yeah, but the problem is the the 2 is the minimum, okay? So we have to avoid them to be stuck in the same minimum. Okay, so then we use some strategy, for example, different input points, of course, that will like guarantee also, but different time constant or step size. We will not change the set of equilibrium point for the dynamic system, but it's just change the trajectory. They move to different input points, then they compare. Okay, then we know who is better, who is worse. That is some strategy, not guaranteed. Okay, but still we have a last result is a mutation. Mutation is the key word. That is a little bit blind. Using operation research also machine learning, different name.
Yeah.
They try if the same, they have to take the different. So then they can proceed. So that is some strategy, no theoretic guarantee, but it works.
Sorry, I have a question.
Yeah.
So I didn't quite follow how the neural network come into the picture of the algorithm. So the dynamical system you presented look like a first order or second order type of algorithm.
Yeah, first of all.
So how is this different compared to a classical first order algorithm or second order algorithm?
Yeah, let me see. Yeah, for example, this one. Okay, this is the This is the one neural network. With the X is actually dealing with the what we call solution. In the state variable.
So X is the decision variable of
Yeah.
the optimization problem.
These
Right?
are like non-multiplier or different variable.
Yes.
So let's deal with constraint. Equality constraint. This is actually projection operator. So let's try to convert. You convert to local minimum. If this convex, you go global one. But this is also corresponding to Lagrange multiplier.
But
You-
how does neural network come into this picture? I can initialize lambda mu and all these variables and just run this dynamical system without neural network. Am I missing?
So
this?
yeah, this dynamic system. Okay, so you can see this kind of active function is like piecewise linear. It's actually rule, like a rule function. Right? I mean, this piecewise linear function is a typical neural network active function. Same thing here. This is rule, right?
Okay.
Okay, well, this one now this is equality function. But this is this is nonlinear dynamics with specialized kind of nonlinearity. It's we call neural network. It's efficient, right? The whole neural network is something like this also.
Sure.
Yeah.
Is this the correct interpretation that if you took that nonlinear dynamical system and for the moment, let's say we discretize in time, and you made a graph of it, then basically running that dynamical system forward can be seen as just evaluating a recurrent neural network. Is this the right interpretation?
Yeah, you can see so, yeah. Yeah, anyway, we search, it's a dynamic search problem. Of course, this system can be discretized. We have some discrete version, that'll be more digital compatible. But then for analysis, it's better have a different equation or different inclusion.
Mhm.
So to be added, to be for analysis of stability. Okay, sorry, then.
Sure.
Let's see here. Okay, yeah, for some nonlinearity, special nonlinearity, we can have this, called duplex. So in order to minimize the spatial complexity, of course, larger population is better, it's coverage high, but the two is minimum. But in order to, you still have danger of the stuck in same local minimum. Okay, sometimes we have a two patrolman, the policeman, or sometimes we need a big team, right? Anyway, that depends on complexity of the problem. So the population size, this is that case, we can two possibly can solve, but it cannot be less than two. So how many population, how big the population depends on the complexity of problem, and also depends on the neural network itself. There are many neural networks can be used in the selection process. For example, we use Hopfield and also Hopfield network, and also use the Boston machine in some specific case. Still, Hopfield networks and then come back in our framework. Yeah, so for discrete variables, binary coded or this, bipolar coded can be changed to encoding constraint or encoding constraint. Actually, the encoding constraint ensures the variable will be binary. Okay, here we choose the additional variable b. To help to make sure this is also the same dimension with the x. The e is the letter one, vector one, 0 is vector 0. Anyway, so this is a many choices came down, coded with 0, 1. So then we eventually convert to decrease mixing zero problem or commutative problem as a global boundary problem. Then we can solve this even like this. Okay, this is the treatment we do, but it's one way to do this. So now in that case, we have another way to do this is using a heterogeneous neural network. Instead of using continuous variable neural network, we can use the both discrete neural network with both discrete variable and continuous variable. So for example, recently we use the Hopfield network, discrete Hopfield network for binary variable, and also project neural network developed by us to with the relu active function or piecewise function for continuous variable. So they work together to find solution together. Okay, because anyway, individually each pair they only find the local solution. So we need a population, then we try to find solution. For example, we use this one for fitting ventilation air condition system application recently. Find this optimal solution successfully, efficiently also. Anyway, so the paradigm for solving many problems in our lab for a year. For example, non-negative visualization for signal processing, feature selection, and also constraint classing. For example, this is a systemic supervised learning, and also supervised learning, and also polyphonic session in China. We have worked on this for more than 5 years, but still interest. We are still doing this now, but also smart application. For example, signal processing, image construction. So we got the copyright standing quickly. Vehicle technology is related to this talk, probably today. We will talk a little bit, and also MPC. This is we deal with a lot of vehicle control. That is also with this heating, ventilation, air conditioning control. We for chiller loading and control, we use the MPC also. Basically this is process control. For vehicle is motion control. Okay, yeah, some of us topic maybe talk a little bit for sparse regression, sparse basic regression. So basically, this is the interesting topic. We have many applications. Basically, we use this also for index tracking, financial index tracking for partial duplication of system. So 50 years ago, we have this new loss function derived based on the Bayesian optimization and also major minimization principle. Okay, basically this is a original variable W vector. We introduced some other variables, sigma and gamma, which is the distributed variables Together with this, we have U law function. This function guarantees sparsity of W vector. That is for regression, and also we minimize this norm, we normal this linear regression. But this due to the existence of sigma and the gamma, this is actually definitely non-convex. Okay, so we have a global foundation problem involved with the W, sigma, and the gamma. So actually, we try to analyze this slide, basically based on some simplification. We see this is actually right our object function. Of course, it's better than the L1 normal. L1 normal is slightly producing, right? But this is much better. So we did a comparison with the other method. Actually, in terms of algorithm, we have two objectives. We also have an optimality, minimum better, smaller better, right? And also we work on consistency. Every time we stuck in the same power pocket. So this is actually here we use the two neural network and equal two is the minimum, right? Based on space regression, the sparse Bayesian regression learning actually. You can see here dark red and dark red dot brown dot always here. Okay, some of covered by other color, but not as this. The red one actually is very fit with equal to one, only single neural network. So of course that's inconsistent. Sometimes good, sometimes not good, because it depends on issue points. Okay, some good points, then they have a lucky here. Some of not lucky are far away. Some green one is also up and of course other two, of course some consistent, but not as so good as that. So this actually a 100 random sample, just compare each other. So for sparse signal reconstruction, we have an original signal, we can recover perfectly with the two neural networks. And also some other method will need some parts. Okay, so this is not a good. We did some stack study with the different signals. So you can see we have a 100% standard width and a 0 standard deviation, even though we only use two neural networks. Of course, it's only double the complexity, but the result is much better. If only one, actually is this one, 75%, sometimes lower. So anyway, we need a partner that help a lot. Also, we use this for PDE discovery, or we can sometimes call identification. This can be do for ODE. Some people for ODE published in Nature last year. But anyway, so just discover the coefficient, and also 0 or not, or some other value. We can find it perfectly, 100%. But in this case, we need more than 2. For example, here we need 10. Fine. So basically, we try this backward. We increase the population size to see the 7 weeks. If 2 is the minimum, we try. Okay, for example, 105, 57%. This is like something 80. But we increase it by 5, then you see 2, then okay, right? So of course, this empirical study only show the scale. But if we increase the population size to 10, then you can see, okay, everybody 100%. Okay, we big population, then we work. So 50, we don't need that. But anyway, it shows that. Okay, this is you mean basically the population size depends on the complexity, and also depends on search, the neural network itself. And many other issue points probably. So for other applications, we sparking neural network. We try without testing error. We increase the population size, number of sparking neural network from 5 to 15. You can see at this point we have ample point, right? So meaning after 15 sparking neural networks, so the improvement can almost flat. No, this is this is not our web spot, but the spark probably is the population of them, but still at this point turn around. Okay, anyway, so we have a lot of study using this patching, also based on the regularization, it's called drop-off regularization, to enhance the generalization power. So in this case, sometimes testing error can be 100%, but too good to be true, right? But sometimes 93%, because this drop-off, enhance regularization, help the generalization power. Okay, also yeah, we can have a lot better result. Anyway, someone asked me to with transportation, maybe it's toy problem, but anyway, I try to prove the concept. So basically, the task assignment to assign group agent to a group task for vehicle, for example, of either transportation and parcel delivery, or some other thing. Okay, or search and rescue, some other operation into task assignment. So we have a, autonomous vehicle a lot, if we need to do this assignment, from top down. So basically, this is a simple combinatorial vehicle, for the big dimension. So we have a assignment, or no, this is a vision variable. So we have has a different scenario, with two vehicle work together, you can have it more. So in two, in that case, this will be like quadratic assignment, but with many constraints. With two quadratic term, a linear term, with cost function, the higher better, the maximize, with many constraints, so with the interpoint, so and collaborations. So this is typical improvement. For example, we have this iteration after loop with a collaboration reinitialization, so you can see the performance increase. Okay, that's good. Sometimes continue improve, sometimes steady, depending on the different pair. Okay, so this is random choose some of the pair for the task, number of tasks, the number of vehicles. Okay, so this is steady with for example, this means two vehicles, some of it means only one vehicle. So it's all scheduled fulfilled. So we compare with many other studies, the first column is our result. The higher better, of course, we always higher than other, in different pair of the scenarios. And also some other similar tasks, we like, also is, iteration with is finding the temporary, so we can have a better result, much better. Cost enough, sometimes enough. So this is we go schedule with a single one and two pair. So of course we can extend to do more than one, two, so there's nothing. Anyway, we have always better than other result in the literature. Okay, some other parcel delivery, the same thing. This is a simple case, right? Almost converting in seconds iteration. So then this is a task aside. Last one, but not this is a cooperative surveillance. So this is sometimes simple, quickly to convert. Sometimes need time, much more iteration to evolve. So this is the final assignment. So we also compare with this is comparison with other results. Okay, later on we have a new paradigm based on, this is a compare with the search, rescue, tracking attack, auto delivery, so this is collaborative neurodynamic database is always high. Scientifically not zero, but of course we don't have a big population. If we increase the number of population, we can reduce this to zero. But sometimes we have but anyway, it's much better than other result. And also we have a new paradigm. Later on we have another one with the H. This is based on hot unit. Instead of projecting our work. So this is year right after. This is 2020, this is 2021 during pandemic. That one you can even better. So this is sensitivity can be zero sometimes. But anyway, depend on the combination of the sample, vehicle and number of vehicle and number of the task. So this is the with different problem we have this is even better or at least equal for projected base. So this is one. Anyway, this is a
Question.
Yeah.
Question about those comparisons, so these benchmark problems, it seems they're all mixed integer programs, right?
Yeah.
Are they also multi-convex?
It's
Or just completely not?
It's a quadratic, this could be non-convex because the quadratic object boundary is not guaranteed to be convex. But but non-convex is less important, less problematic than discrete
Yes,
of the variable.
we have the hot field network to help with that.
Right, well, anyway, okay, so we also deal with the TFP, but this of course is. This not change, anyway. Okay, anyway, so this title I checked this one somehow different. Okay, anyway, so we have some strategies. So this classical one, we deal with this one. This is based on some age. What is representation or whatever. Okay, basically HIGA is in I stop just stop city. But this is good because it's simple function. Without if you deal with age representation, we need another some other function to avoid the loop, simple non-connectivity. This actually how we use this in 1980. Okay, so but anyway, so we know many so this matrix have a lot of variables, right? N by n. We need to reduce the complexity by filtering out some of impossibility. Right? Because some of them are definitely not possible to be considered. So we filter out some, so we replace some of some strategy. So that will save a lot of time, to avoid local minimum and also reduce complexity. So this actually become Kupa, quadratic unconstrained linear. Okay, this is of course still not yet, because this is a quadratic object function with a equality function and with the quadratic equal, linear equality, quadratic equal. Anyway, so we need to add a penalty to provide penalty to become this is become eventually become a core and quadratic unconstrained binary optimization. So this is of course n by n, but many problems are being avoided. Yeah, so this yeah, sorry, this is all version, I'm not changing yet. Anyway, so by using Hopfield network, so this is all one discrete Hopfield network. With this simple active function, we can minimize this problem. Okay, this is general one with W and theta. So this is guaranteed. This is 1982 work, not long time ago. And also we use different model. For example, this is called Hopfield network, discrete Hopfield network with the momentum. With the addition we use here, this one can be synchronized. Before this had to be asynchronized, updated, but in order to guarantee the minimization, but this can be done synchronized. So all neural network with either mission variable or vector variable can be updated activated synchronously. So that's the same time. In addition, we also use a Boston machine, which is overall by Jeffrey Finland. This is another number rate. But this have some local queue climbing property, so we can climb locally. But that happens to find a better solution. So anyway, so we also added our framework, so we can do this multiple neural Hopfield network, Boston machine work together. Oh, sorry, this is also the topic that I had skipped already mentioned. This is how to avoid local minimum. Yeah, this is all. I already checked, but somehow I missed out the version. Okay, so we have some small toy problem benchmark. Basically, try to find a solution. Okay, compare with some other result. Okay, this is of course optimal solution. This is a known solution. This is our result. It happens to be same. Some other result not good. You can see this is a messed up. This is a better one. This is a auto solution. This is our result. Almost same, but the other solution is not. Okay, this is the last one. But still low scale, small problem. So of course, they can be solved by using big computer, but we didn't do it. This is a still toy problem actually from TFB with 220 CD. So we have optimal solution using this Boltzmann machine with the momentum of how quickly we can. Anyway, this is the optimal solution with small standard deviation not zero because the population size will be increased. So this is for TFB for trajectory planning of vehicle, autonomous vehicles, which is essential. We did a lot of work recently using this neural network for under the receiving horizon framework. For basically, we formulate the formula as the receiving horizon global quantitative problem with the weighted quadratic navigation function as a project function, and also optical avoidance constraint. That's the necessary. Yeah, we solved the problem sequentially. In the minor rolling window, using neural networks, many neural networks, for planning. So this is the object function to be original one to be considered. With here is the position actually, P bar is the waypoint vector. And also this is T is the capital, the prediction horizon, TC is the control horizon, like MGT. Okay, with the vehicle type, this is kinematic, this is a kinetic vehicle, this is a safety set with the point have to be in the boundary to avoid the colliding with the optical on the way. So this is a terminal and also or upper bound, lower bound. This top T is top is for vehicle. We also consider this vehicle techno dynamics involved. Okay, so this is actually we use the internal lava because this one does not have a V in the object function. So because they can have a set, could have a chattering problem, at terminal point. So now we add this one as a vehicle display to along with other constraints can avoid this shattering problem. So that is small change. Anyway, we develop the algorithm assuming the reformative problem, and also it proved with some language theory here to be feasible under some minor assumption. Okay, so yeah, that's also we also have a specific condition for two scenario. I'm on the vehicle and the DSV. So this is some experiment result with upper bound, lower bound, right, line, and narrow cross. But some of the other, for example, discrete sampling method processing, they have some violation of constraint. So, but in our method, we never cross border, cross the line. So this simple scenario we try to illustrate how difficult career we can maneuver over with different issue point. So of course it's toy part, but it's try to prove the content. Also we have another, this is a so this is control input, talk is from talk. So within the bound, we call the too big we cannot achieve. This is actually this is also output is output actually. Also within bound, but some of them other line is not our result. It's DSP, it's discrete sampling problem. They avoid, this is for some certain vehicle, like marine vehicle. Also, we have a lot of projects work on this terminal vehicle in team. We have a number of them in parallel. Of course, here we have a trajectory planning and also for guidance. And lastly, we control. This is because here automation can take place here. Is this level or this level? Or sometimes this level, but this lower level will be more safe. It's safer actually. For terminal marine vehicle. This is object function to be considered. With the first function is actually formation of the vehicle with a certain distance. Second one actually is an obstacle avoided. So here we use the control the barrier function as a optical avoidance magnitude greater than 0. Last one upper bound, lower bound. So this is new one last year. Actually I have some new coming, but so sorry, this is not on here. Anyway, we prove we have some theory, prove the input to state here. This is a scenario with 4-way ASV with 3 optical and wave. So they have to, in order to move from here to there, they have to change the position with some certain distance. The distance gets smaller, but anyway, still pass through the optical. So this is some step in the beginning. So before they follow almost straight line, but they have changed somehow to avoid the optical. Then they move to another optical tool here, then another one. Eventually pass through the goes to the goal. Okay, so this is actually descent to optical. Lower bound, red line the minimum margin, safety margin. So we never cross the lower bound. So all 4 vehicles. So this is between ASV, including themselves, and also 3 for disturbing, I mean, obstructing ASV, you can see here. Yeah, some of small obstacle, sorry, some other ASV becoming this big, try to this, big mess of this one during the process. So this is our team, but this is a obstacle, moving obstacle. So, but then we keep a distance also, ourselves and other ASV. This is red line never across, sometimes you attach on, but not the cross. So this is about the 3 meter, the distance we will keep. So this tracking arrow, tracking arrow cannot be 0 because sometimes we have to bend ASV to make a shorter distance, avoid the obstacle, but it's okay, right? Because the meanwhile we keep the formation. So keep going, yeah, we also use some hardware in the loop experiment, so the similar firewall can be verified, but we didn't do a real hack, I mean, a real full implementation, only hardware in the loop experiments. Because that was during pandemic, we submitted. Anyway, sorry, my time is up probably. I try to conclude in the next final slide. We have proposed a paradigm which is both biologically and socially possible. Biologically, we have a neural network resemblance, more or less. But socially mean we have a partner, when we have collaboration among agents, or this neural network can be considered agent. And also, oh, okay, good. They have desirable property, because it's not a heuristic. We have a heuristic in the upper level, but we have some theoretical guarantee convergence, right? So almost sure convergence. It's not a. This is better than without any guarantee. The almost sure we have with some higher assumption. It's sort of bridge between neural networks and also evolution computation. This kind of hybrid intelligence, right? Also hybrid informing intelligence. Anyway, I would say collaboration is the key here. Without the collaboration among agents or neural networks, we cannot achieve success. Okay, collaboration here is information sharing. Okay, so we have some desirable properties. So collaboration play an instrumental role. In many applications here, actually property transportation, vehicle to vehicle communication is also to be like information chain. So we have a lot of many projects with other things like AI powered heating, ventilation and condition system actually done. And also AI powered synaptic technologies to ongoing. And also we have a new project on AI powered robotic surgery robot and also underwater robot funded by Hong Kong government this year. So that's all in the organization. Neural network can play a role there, hopefully. Thank you for your attention. Yeah. Any attention or maybe a comment, suggestion? Welcome.
Yeah, we have a few minutes for questions.
So I'm wondering if there's a general way to decide how many models, how many neural network to be collaborated for some task.
Yeah,
or
this
is it-
Yeah, it's a very natural question. Yeah, I know. It's just like a hyperparameter in number layer, deep neural network, right? So it's difficult to tell how many layers needed. But here, fortunately, we don't need the stack up. We also separate them. They are not connected. They work on their own. But the information change, of course, more people want to provide more information better. So basically, this hyperparameter depends on the complexity problem. The more complex problem, you need more power. And also depend on how good the neural network search. If I have some outfield better one, the search find a good point, then we don't need money. Right, so then, but that's the and also some other thing, some other information probably can help. Some sampling, basically we treat each local minimum as sample. Some specific like basic, we can build model, yeah, this one can do. Also, machine learning can help, to find a better each one at least, or maybe next round also. But that we didn't do it. We did it, but not published. Yes. Yeah, but that is the machine learning for optimization, yeah. But that takes time, yeah.
I'll ask a question. So I'm, super intrigued by these neurodynamic methods to solve difficult optimization problems, particularly combinatorial ones. And, recently our group has been studying just purely deep learning methods to solve, say, the traveling salesman problem. I'm wondering if you looked at those methods where they're using just pure deep learning to produce, given the current path, what is the next edge and the shortest path versus, what you're talking about here, which is ultimately formulating a system of dynamical systems that is converging towards the optimal solution. Can you maybe comment about what you see? And I imagine you review papers on this.
Yeah, deep learning, of course, is popular and also amazing, but I think in theory, actually, in principle, if you can build deep learning model for parameter optimization problem to optimal solution, but take costly, probably the cost is high, super high. Sometimes, it cannot afford. It's just like Oracle, right? You can map the parameter to the optimal solution to learn. That is, it's not, it's mission impossible, maybe it's very difficult, actually. But here we tell you we don't do learning, we do this real time searching. That's the traditional optimization doing.
Right.
Without but of course this model can, the new problem has to research again. Hopefully, you can borrow to learn something. But of course, the training on deep neural networks, they can have, but I think we're time consuming, of course. But
Right.
it's not guaranteed either.
Yes.
But it can happen something, but because unless you have all problem sample already in the training set. Otherwise, some new problem it cannot be predictable, right? But here, of course, we don't care about we just give them problem research. We can find the local people, then it's iterate again.
Yeah, no need for
It's not-
training real time.
Yeah. It's more traditional than deep learning, but deep learning, of course, it can be leveraged to use, finding some unique points. Maybe not optimal, but it depends on how much effort you.
Thank you, Matt.
Yeah, I think that's more practical. If you have it's difficult to find build a deep workflow model, the auto solution company don't have it. Yeah. But it's in theory, in principle you can, but if you have a lot of data, a lot of computer power, lot of time, that's the possible. But I don't know if it's practical or not. Yeah, please, yeah.
Yeah, we just very nice talking to you, and I just have like some kind of following comments followed by.
Yeah, okay, so.
Yes, so basically, I think it's very interesting about this neurodynamic optimization framework, and also think like it would be very interesting to include deep learning inside. So have you ever considered that to have this kind of like physics informed learning methods, like you combine the neurodynamic style like into a learning framework, so to like to reduce the computational cost and like embedding this like the knowledge into the model.
Yeah, we always consider, but it's a time clock. Actually, he's a schoolmate, very Minhua Chen, my colleagues in SCU. He's doing power in there, but purely using neural network for prediction, but not pursue random, in a range, but not optimal. It's just like each point something. We were talking a lot, we collaborate together, but we never did it seriously. But of course, everything have a pro and con, so we need to combine both of them. But given the popularity of neural networks, deep learning, so I'm always true to do this. But we don't have enough manpower to do this.
There's a hand online too, just.
I was just gonna say,
Question?
yes, you had a question, you're muted, by the way.
How to read this question?
Oh, he should.
He should be speaking, but if he, is that Lejeune?
Yes.
Yeah, can you hear me right now? Yeah, can you hear me right now?
Yep.
Oh, okay. Yeah, I just have a question about like you just report the distance when you use this kind of methodology on problem like TSP. I'm curious about like you just report the worst case and the best case. I'm curious about like what's the optimal gap like between like for this kind of task, how is the performance and also the solving time of it?
Which problem you mentioned? Any general or specific problem?
I think any of the synergy.
Oh, you mean a
He's
company?
asking about the optimality gap and the solving time.
Okay,
We measure
so,
that too.
yeah, that's the issue. Of course, the big problem. We have actually we didn't use the 3R computing devices. We actually most of my students only use the laptop because they are not efficient enough. So we didn't even use a GPU. So, but it still managed, we are dealing with let's say chiller system, which is a smaller scale of power version, electrical power system. This is all problem can solve in matter of minutes. Because, server system is pretty slow. In terms of minutes, then hourly it will be okay. Yeah, but of course, if you want to have a transportation system, which is electronic system, you need a lot of computing device on board. Like even a terminal service vehicle, marine vehicle. So, but yeah, we need a lot of computing power to do this in terms of the we didn't do actually worst case study. So we have a
I mean, I just
which
curious
of course
about like
requires.
maybe the average optimal gap.
Oh, for TSP, for some for other general problem.
Yeah, maybe like June, because we're over time, I'll say, I think this is a good thing to read your individual papers. And
Yeah.
Okay, yeah, thank you.
I
Oh.
I have one last comment.
Yeah.
We'll follow up later. This stuff Scott is much better expert here than I am. So I can get into trouble very easily. I'm curious on use cases here. In particular, and I'm not there yet, but I'm curious, is there any way that we can modify this collaborative neurodynamic approach in particular to help create better tests and monitoring for AV services? I will say this is one of the biggest concerns that I keep on hearing in the field now. As regulators, we can't give an AV a driving test like the DMV can give me a driving test. So how can, say, the state or federal government set reasonable tests for AVs that cannot be beat? And maybe the answer is no, I'm totally off base, but I just wanted to bring it up because that seems to be one of the biggest questions right now, especially around this.
Okay. Yeah, I'm sorry. I was, to be honest, I'm not in the.
I know.
Publicity.
I totally, yeah, yes, but mostly what I'm talking about is. I guess maybe a better way to put it is just using neural networks in a reverse way. So as opposed to trying to get them to converge to a solution. Scott, please tell me if you can say this better than I am, or if I'm totally crazy here, but trying to create a testing environment that is non-deterministic so that you can ensure that a variety of different each individual AV company has their own, say, virtual driving system that they're going to be operating in. And this is a big need from regulators, is to be able to give them a test to feel that, okay, this vehicle is operating in a safe fashion without them basically designing their vehicle around the test, which is already what happens, say, for emissions testing. Those have been extensively gained already to, vehicles now, for example, their transmissions are designed in such a way to pass EPA testing.
Yeah,
Scott, tell me if I'm totally crazy here. Yeah.
No, I mean, I think it's really a question of how can we use this theory and methods to solve these application problems? Do you see a way to link?
Yeah.
Yeah.
As I said, I have no idea what this.
We'll talk, don't worry about it, yeah.
For the government regulation in
Yeah.
especially California or US system. So right now it's pure It's just like full concept in the paper.
Yeah.
So we don't have a apply even,
Totally,
all in the laboratory setting, yeah.
totally understand. Thank you for humoring me, I appreciate it.
All right, I think this is actually our last seminar of the term, so thanks all who attended. And there might be some more past seminars in the summer, we'll see. You know, but at the very least next fall. Thank you,
Yes,
Professor.
thank you.
Thank you.